We have come to the last set of videos in the stochastic processes playlist, and here we'll be considering modern topics in stochastic processes. And the first in that series would be the hidden Markov models. Hidden Markov models. So let's go for that. First of all, a hidden Markov model, HMM, is a probabilistic model for sequential data where the system has hidden states. We observe outputs generated from those states. So interestingly, I'm currently applying this to one of my research where, you have a time series data, and in that time, even maybe not time series data, even any kind of data at all, you can actually regroup the data in such a way that you can find hidden states in the data. So you can find different regimes in the data. So the key idea here is that, first of all, we observe a sequence. Let's say you have sequence O, which is O1, O2, up to OT. But the true states are actually, you have true states like S equals S1, S2 up to ST, which are hidden, right? That's the basic idea in hidden Markov models. So a very good example will be you have hidden states like rainy and sunny, whereas all you're observing is maybe you're just talking about walking, shopping, or cleaning. But while doing that, it might just be rainy or sunny in the background, right? So we only see activities, but we do not see the weather. So if somebody tells you, what are you currently doing? You might just say maybe you are sitting or you're walking or you're shopping or you are cleaning, whereas it's raining outside or it's sunny and all that. So the rainy and sunny states are like hidden states, while the actual things you are doing are like the observations, the things you can easily refer to that you're doing. So let's talk about components of an HMM, that is a hidden Markov model. So an HMM is defined by, first of all, we talked about the states. You have states S made up of different states S1, S2 up to Sn, and you have observations O1, O2, all the way to OM. Then you have transition matrix. Of course, this is a regular feature of stochastic processes. So you have transition matrix Aij, and it gives you the probability that S sub t equals J, given that S sub t minus 1 equals I. Okay, and then you have an emission matrix where you have bj of k equals probability that the observation at t equals k, given that the state at t is equal to j. And then you have initial distribution, which is pi I, and that is probability that s1, that is the first state, is equal to I. So we can actually simulate this right here. So here now imagine you talk about states rainy and sunny, and then you have observations walk, shop, and clean, and then you have initial probabilities pi. That's the initial distribution we just looked at here. This initial distribution here. So that is why when you're starting out, right? The pi will be 0.6 and 0.4. And then transition matrix is 0.7, 0.3, 0.4, 0.6. Of course, what it simply means is that, rainy, sunny, right? Probability that if it is rainy right now, it will still be rainy at the next step is 0.7. So rainy, sunny, probability that if it is raining now, it will be sunny next is 0.3 and all that. So then, of course, I mean, 0.4 means probability that if it is sunny night, it's going to be rainy next. And 0.6 means probability that if it is sunny night, it's going to be sunny still. That's 0.6. So, and you have the emission matrix where you have 0.1, 0.4, 0.5 for raininess, and 0.6, 0.3, 0.1 for sunniness. And you can have the observed sequences walk, shop, clean, and then you can map that. So you have observations I for I, observations in enumerate your observations, and then you have observations index. So you have OBS map O for O in observation. So if you print the indices, then you can have 0, 1, 2. So if you print that, you have 0, 1, 2. So you then say workshop and clean are like your observations. And those are 0, 1, 2. 0 is 1. I mean, 0 is work, 1 is shop, and 2 is clean. Then we have fundamental problems. uh, Three fundamental problems when we talk about hidden Markov models. We have the idea of evaluation. So we want to compute probability of an observation given the given lambda. That's given lambda, and then there's so after evaluation, you talk about decoding. In decoding, you want to find the argument for the maximum value over S such that for probability that the maximum argument over S so for the probability that if there's a particular sequence given a particular observation, and then you have learning. So in the case of learning, so you estimate parameters, so you have A, B, and pi like that. So, and then in 54.4 we have forward algorithm for evaluation. So we can define the alpha of t at state I is equal to the probability 0 observation 1 all the way to observation t, and then state t is equal to I, right? So you have all these observations given that state t is I, and then at state t equals I rather. So step one, you have initialization. So you have alpha 1 I, that is pi I bi into observation 1, and then you have the recursion at of j, that is summation over I alpha t minus 1 over I aij bj o t. Then you have termination, probability of the observation to be summation over I of alpha t I, like that. So we can run that here. So running it now, you have this alpha matrix. So 0.06, we're talking about alpha. We talked about this alpha t of I up here. So you have the alpha matrix here. So that's 0.06, 0.24, 0.05, and you have all of that, right? And how does that come about? You define a function forward with pi a, b, and then the observation index. Then n talks about the length of pi. T is the length of the observation index, and then alpha is 0 t by n. Then you initialize like this, and then you have the recursion. You run alpha and all that. So if you run this now, if I run it again, the probability matrix might even change. Okay, you see it keeps changing like that because it's of okay. Now as you keep running it, it ends up converging at the end of the day. So this now converges to 0, 0.6767 and all that. And then the sequence probability then ends up being 0.22222222, like that. So then we have the Viterbi algorithm talking about decoding. So we compute the most likely state sequence to define this delta t of j equals the maximum of delta t minus 1 at I multiplied by aij, then multiplied by bj of ot over I, like that. Then you have the back pointer. You have psi of t, psi sub t of j equals argmax I into delta tii aij. So, and then Python brings it to life beyond the mathematics, right? So we define function Viterbi with parameters pi, a, b, and the observational index. Then you have the n, that's the length of the pi, and t is length of observed in the indices or so. Then you have the initialization here, pi b into all that. Of course, I believe that's this formula you have right here. And then you have the recursion part of things. You have the recursion right here, and then you have the backtracking. And then if you run it for most likely states, you have, so this is sunny, rainy, sunny. So if I run it again, so it's still rainy, sunny, sunny. So I think it's, in this case, it's fixed like that. So we have that sunny, rainy, sunny is the likely probability. Then we have the idea of backward algorithm. So if we define beta sub t of I to be probability observation t plus 1 all the way to ot, given st is equal to 1, given that the initial sequence at any time is equal to 1, then you have the initialization, that's beta sub big T of I equals 1, and you have the recursion beta sub small t of I equals summation over j of aij bj o t plus 1 b t plus 1 of j, like that. And then we can also run this here. So you define a function backward, that's the backward, I think, yeah, for the backward algorithm. So you define that backward stuff with parameters a, b, and obs index. Then you talk about n, which is a shape of O, and t is length of the indices. Then you have beta. So for t in reverse, you now do, so you specify that formula, all the beta t plus 1, all this kind of thing. And then the idea is to return beta later. So beta is backward AB. So AB and OBS underscore IDX. Then you now print the beta matrix, the beta matrix like that. And then you have this. So if you keep running, as you keep running, it goes towards, it converges at the end of the day. Now you can see this is 1.10 raised per minus 25, and that's as good as zero. So this is zero right here, and this is like this is 10 raised per minus one, that's 0.33, and this is also 0.33. This is zero here, this is one, and this is also one. So this is zero like that. So as you keep running, it converges towards a value at the end of the day. Then we talk about posterior probabilities. So for posterior probabilities, talk about gamma. That is gamma sub t of I equals alpha sub t of I, beta sub t of I, all over p of 0. That's p of observation. Then for psi, you have psi sub t of I comma j. That's alpha sub t of I, a sub ij, b sub j of o sub t plus 1, beta sub t plus 1 of j, and all over p sub o, p of o, like that. And then you can compute the gamma with parameters alpha and beta. Then you take the probability, which is the sum over sum from the back, right? Alpha minus 1 means you're summing from the back, and gamma is alpha times beta divided by the probability that you have up here, and then you return gamma. So gamma now be gamma computes, take alpha beta, and then we run this. So as you keep running, this ends up converging to 0, 1, 1, 0, 0, 1, like that at the end of the day. Then you have the Baum-Welsh learning. So we have update rules. Initial, you have pi I equals gamma 1 of I. Then for transition, you have aij equals summation over t psi sub t of I comma j, and then you have summation over t gamma sub t of I. Then you have emission, beta sub j of k, that's summation over t, such that ot equals k for gamma sub t of j, and you have summation over t of gamma sub t of j, like that. And then we can you know you can we can demonstrate that using this length. This is a very long code here, to show all those things step by step. So here, so you define the function forward with pi, a, b, and the observation. So n is length bi and t is length obs. Alpha is np dot 0 t comma n. And then you have alpha of 0, pi, beta, obs. Then for t in range, you have all of this. Then you return alpha. You can define backward a, b, obs, all that. Then, so for the Baum-Welsh part now, you have list of observation indices, that's OBS. N is number of states, M is number of observation symbols, and N iter is number of iterations. Then you have T, length of the observations. So you have random initialization, that's np dot random dot seed 42. Pi is np random rand, and all of that. So um, you go all the way down. It's a pretty lengthy thing, and then we end up getting we get B, we get for so okay, we have series of iterations, by the way. So each iteration gives the value of pi, a, and b. So as you can see, we always have that pi and all this pi, a, and b uh as the parameters. So pi, a, b, and then you have the number of observations there. So here you have, this is for iteration one now. You have pi to be 0.03, 0.96. Of course, the two of them must add to 1. Then you have A also. These two must also add to 1, I believe. And this is 0.05, 0.76. So if this is 0.5 and this is 0.76, this is 0. No, this is 0.05. This is 0.19. 0.1 plus that's 0.24. So everything here must also add to 1. Then so you have iteration 2, iteration 3, and at the end of the day, you have something the value is tending towards. So at the end of the day, the value is at iteration 10, pi is now 0, 1, and then a is this is more as good as 0, and this is 1, this is 1, and this is also 0. And then here this is 0, because if you have 3.67 times 10 is for minus 25, then that's as good as 0. And then you have 1.00, 0.00, like that. So this is simply 0, 1, 0. This is 0. Okay, this will be 0.67, and this is 0, and this is 0.3733. When you add them, you still get 1 there. So that's the concept for the Baum-Welsh learning. So we then go ahead and try to round that off. So here now we have the key takeaways here. We have that hidden Markov models, HMM models sequences HMM, hidden Markov models, models sequences with hidden states, and there are three main algorithms. You have the forward for likelihood, the Viterbi for decoding, and Bombosh for learning. And then we have applications in speech recognition, NLP, that's natural language processing for POS tagging, and we use it in bioinformatics and of course in finance. So there are some important assumptions here. So we have the Markov property. Of course, the Markov property simply tells you that the next state is only determined by this current state. The states before this current state do not matter in determining the evolution of the system. So output independence, you have probability that observation at t, probability of observation at t given sequence at t is simply the same thing as probability observation of t at t given s sub t. So we then have okay, this should actually be, I like to name this practice problems as usual. Practice practice problems. So we have that. So there are some conceptual questions. Um, so explain the difference between hidden states and observations in an HMM. Like we've said that already. Observations are like you're sitting, you're walking, and all that, but then they are hidden states like maybe it's raining or it's sunny. They state the Markov assumption mathematically and explain its implication. Well, Markov assumption simply says that the next state is only determined by the current state, and the states before the current state do not really count in determining the state after now. So what independent assumption is made about observations in an HMM? List and briefly describe the three fundamental problems of HMMs. We have all that listed. Why is the naive computation of probability of observation given lambda computationally expensive? So, and then we have some basic computation given pi is 0.05 and a is that compute p is s of 2 equals 1 and all that. So we have all of these questions there. Um, yeah. So you want to check them out and see how well you can operate with them. So let me flash the questions from the beginning again. So here we have questions, conceptual questions 1 to 5. For basic computation, we have, okay, I think that's, I can show them in twos or so because they are a bit long. So you have basic computation 6 and 7, then you have 8, 9, and 10, then you have 11 to 13 for forward algorithm. You have a Viterbi algorithm. You have 14, 15, 16, then 17, 18, 19 for backward algorithm. 17, 18, 19, 20 for back. Okay, yeah, for backward algorithm, you have just 17 and 18 actually. Then for learning for Bone Welsh, you have 19 and 20. And then there's a bonus challenge. Explain how hidden Markov models can be used for part of speech tagging and what changes if observations are continuous instead of discrete. So you want to check all of that out. And with this, I come to the end of the first video on modern topics under stochastic processes, talking about hidden Markov models. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos first or getting to see some videos exclusively, and of course, you can request for PDF copies of my notes, or we can hang out together to discuss whatever interests you on my channel. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.